Okay, so a quick recap from what we spoke about last time, which was mostly eigenvectors and eigenvalues. So the key equation from the last session was this mv equals lambda v. So if there's some exceptional vector v, such that a matrix acting on v gives you a scalar times that vector back, then we call that v an eigenvector of the matrix with eigenvalue lambda. And then we saw this nice procedure for finding the eigenvalues and eigenvectors. You get the eigenvalues by solving this equation, which is simply the statement that this matrix is not invertible, as we saw. That gives you a quadratic, and you solve for the lambdas, and you can plug back in to get the eigenvectors, which you'll see on Matrices Challenge 3, some examples of that. And then for Fibonacci's, we saw that there's this very convenient way of repeatedly applying a matrix. So if you need to apply a matrix M many times, which is repeatedly evaluating a composed function on U, it's much easier if you rewrite U in terms of eigenvectors, because then it just multiplies by scalars. And then the last thing was we saw that for a general 2x2 matrix M, the determinant will always be the product of the eigenvalues. So this thing we saw in session 2, I think, yeah, the determinant was in session 2. We see this has a new interpretation as the product of the eigenvalues, and the trace is the sum. So that was last time. This time, we're going to shift gears for the first part and just discuss kind of qualitatively a very surprising experiment called the Stern-Gerlach experiment, which is kind of the traditional starting point for a study of quantum mechanics. And then we'll see how to use this technology of eigenvectors and eigenvalues to explain the results of Stern-Gerlach and predict possible measurements of an electron spin with their probabilities, which is kind of the classic toy example of quantum mechanics. So that is the plan for today. Questions or thoughts about the review and roadmap?
I have no questions or thoughts.
Cool. Okay. So the experiment I'm about to describe to you is real. This actually happens. It happens for electrons, it happens for silver atoms, it happens for buckyballs, which are carbon-60 molecules. This is not some strange, peculiar property of electrons. This is a universal fact about matter. And I'm going to simplify the results of the experiment by kind of abstracting away some of the properties of matter. So we're going to discuss an experiment which shoots electrons or any other type of matter into some experimental apparatus, a box. And what actually happens when we do that is inside the box there's some magnetic field being applied. So there's a magnetic field which we typically write with the letter B, and electrons have different properties that cause them to move differently in magnetic fields depending on which value that property has. So we're going to send in a beam of electrons, and some of the electrons have a certain property that makes them bend upwards in this magnetic field, and they'll move out in one direction from the box. Some electrons will have the opposite property, and they'll move in the other direction. The actual details of that property are not really important at all. So to avoid distracting detail, I'm just going to replace the names of those properties with words. So I'm going to call them color and hardness. And since both of these properties only have two possible values, they're attributes, so you can just think of them as being, I don't know, +1 and -1 or something, I'll just give them names. So the color, we'll say, can be either black or white. So every electron is either black or white. Those are the only possible values of the attribute. No one has ever seen an electron that was not black or white, etc., etc. That's one attribute. The other attribute I will call hardness, and we'll say an electron can be either hard or soft. Same deal. Either hard or soft, those are the only possibilities. And the point is that we can measure those two properties, color and hardness, by shooting the electrons into one of these boxes, which in reality have a magnetic field, but we can abstract that away and just think of them as filtering out electrons and shooting out one of two ports, a top port and a side port, so that all of the electrons with one property leave one port, and all of the electrons with the other value of that property leave the second port. So for instance, we think of a color box, you shoot in a random assortment of electrons, kind of, randomly mixed of all of the attributes. You shoot them into a color box, and those electrons that are black come out the top, and those electrons that are white come out the side. Similarly, we can build a hardness box. You shoot in a beam, the electrons which are hard come out the top, and the electrons which are soft come out the side. So all that we can do, and the only tools we'll use for the next couple of slides in this experiment, the only things we're allowed to do are prepare a beam of electrons which go in. We can use boxes that filter electrons by which property they have, and then we can measure how many electrons are in one of the output beams. So for instance, we could put a little detector here that measures how many electrons come out this port or in this beam. So one possible experiment we could design is prepare the initial beam of electrons, send it into a hardness box, and then measure what fraction of the input electrons come out of each of those two ports. And the answer to that experiment, as we'll see, is 50% of the electrons will come out of one side, 50% will come out of the other. Because the initial ensemble, as we call it, the initial mixture of electrons had equal values of hard and soft. So that's it. That's the whole setup for the experiment. Input beam, filter by hardness or by color, and then measure what fraction of the electrons come out one of the two ports. Is the experiment clear?
Yes.
Questions about any of this stuff?
No.
Okay. Then let's establish just a couple properties. So I'll tell you a few experiments that were done before the main results of the experiment. So these are kind of sanity checks to make sure that these properties behave the way we would expect. So one property is that these are repeatable. If you measure one of those two properties, which I'm calling color and hardness, in immediate succession, you will always get the same result. What do I mean by that? So we start with a well-mixed ensemble of input electrons, which is supposed to have, equal numbers of all properties. Send it into a color box. And then you filter, the color box filters so that half of the electrons coming out are black, so this will be 50% of the original. Half of them are white. And then we imagine putting a second color box, which is in the way of the black stream. So I put a second color box up here and do the same thing. So you send the input stream of filtered black electrons into the color box. And I claim that if you do this experiment and measure how many come out of the second color box, they will all be black. 100% are black and 0% are white, which makes perfectly good sense, right? Because we first filtered out all of the electrons that are black in the first color box. So you would expect that if you only kept black electrons from the input beam and then measured the color, they should all be black. So hopefully this is not surprising. This makes total sense, but possibly not. So is this statement of this result clear, and or are there questions?
Yes and no.
Okay, good. So another result, empirically, you might think that color and hardness are somehow related, but in fact they are not. They are uncorrelated. So measuring one of these properties, say color, will tell you nothing about the hardness, and vice versa. So let me make that a bit more quantitative. We start with an input beam, well-mixed, equal numbers of all the attributes, filter by hardness, and keep the hard electrons. So the hard electrons go up here. The soft ones we discard. Then we measure the color of that hard electron stream. So if there were some relationship, like hard electrons were more likely to be black than white, for instance, you would expect these numbers to be different. But they're not. If you take the stream of hard electrons and measure the color, again it's half black and half white. So what this tells us is that color and hardness are completely unrelated. Knowing an electron is hard tells you nothing about whether it is black or white. It's still 50-50. So they're uncorrelated properties. Questions on this?
Loud shuffling.
Was that you or a dog or some other human?
That's me. Out of curiosity, stupid question. The two qualities that we are filtering by, are there two real life equivalents?
Yes, so I'll tell you later that these correspond to an electron spin. So these are very real properties that every particle has. I've abstracted that away and called them black and white just to avoid distracting detail about what spin really is. But I can tell you about that later. For now, we just want to focus on what the results of the filtering are.
Okay.
Good question, though. Other questions?
I've known.
Okay. Well, now I will challenge you to predict the output of an experiment. So I will describe to you with this picture a new experiment. We start again with a well-mixed ensemble of input electrons. We first send that into a color box. So you would expect that this, filters at half of the input stream, which is white, half of the input stream, which is black. So you do that. Then you keep only the black electrons and feed them into a hardness box. So as we saw before, color and hardness are not correlated. So you would expect again that 50%, when I write a percentage, by the way, I'm talking about the percentage of the input stream coming into the box, not the original one. So this 50% would really be 25% of the original beam, but I mean half of the electrons coming into this box in particular. So half of the electrons coming into this box, the hardness box, will come out hard, and half will come out soft. So that's just the statement of the previous slide that color and hardness are uncorrelated. So now I ask you, make a prediction. We feed the output of this kind of consecutive measurement of first color, then hardness, back into a color box. And now we measure how many of the electrons coming into this color box are black and how many are white. So I'll ask you, what are the percentages coming out of this color box which are black and white?
Assuming the act of measuring hardness didn't change anything, it should be 100% black and 0% white.
Good. So this is what any reasonable human would expect. We kept only black electrons and only hard electrons, so all of the electrons coming into this box should be both black and hard. In fact, that's totally wrong. In fact, 50% are black, 50% are white. It makes no sense whatsoever. All of the electrons we thought coming into this color box were black by construction, because we filtered out in the first color box only black electrons. And now, after the act of measuring hardness has been performed, as you alluded to in your answer, half of the electrons are black and half of the electrons are white. This is completely startling. It in some sense means that we've somehow contaminated or disturbed the state of the electron by asking what is its hardness. In doing so, we've kind of corrupted the blackness of the electrons which were coming into the second hardness box, and now half of that output will be white rather than black. So this should be mind-blowing already, that the act of simply asking what quality does the electron have changes one of its other properties. Measuring the hardness of the electrons changes the input stream so it's no longer entirely black, and now measuring those hard electrons, you get half black and half white. This is the first very surprising result, but we will see another. But first, questions or thoughts on this so far?
What would happen if you were to, instead of measuring the hardness, just simply let it sit for the time that it would take to measure, the incredibly short time it would take to measure, and then take its color?
By let it sit, you mean kind of you wait for a while in this stream or something? What do you mean?
Like just get rid of the hardness box, but have something happen instead that is absolutely nothing, that takes the same amount of time.
Oh, very good. Okay, so you say, for instance, take half of the electrons coming out of this color box and just send them on like a very long kind of winding route that doesn't measure anything, and then put them into the color box, right? So just a
Yeah.
control, so to speak. You don't measure anything, you just waste time and then send them into the color box. If you do that, you will get 100% black. So it's not the case that electrons, when you leave them alone and don't watch them, they somehow oscillate. They just kind of change their mind about whether they're black or white. If you can wait for the age of the universe, and these black electrons will stay black if you do not measure their hardness.
Okay.
Very good question. Other questions?
I have none.
Okay. So this should be extremely unsettling so far. So I will emphasize again the strangeness of this result, that half of the electrons exit this final box, the color box, as black and half as white. And as you pointed out, this is completely unrelated to the time that has passed between them. It's somehow intrinsically related to the fact that we ask the question of what is the hardness of the electrons that came out of the black port of the first color box. So we'd like to dive a little deeper into this question and think, is there something about the path that an electron takes that might affect possible measurements of its color or hardness? And this is kind of related to the point that you brought up, that we could take something out for a long path and then feed it into a color box. We're going to expand our toolkit of possible experiments so we can ask more questions of that form. And to do that, we'll introduce a new piece of the experiment, which are mirrors. So now, in addition to hardness and color boxes, imagine that you can have kind of these mirrors which redirect the stream of the electron. So mirrors, we will assume, simply change the direction of an electron beam, but do not change any properties whatsoever. So all of the electrons which are coming out here as hard bounce off the mirror, they stay hard, nothing about them changes. It purely redirects their motion. That's all. Same thing here, soft electrons bounce off this mirror and go up here. And then we will introduce a combiner box. And in the same way, a combiner box simply takes two streams of electrons and merges them together. So you can think of this as just forming kind of like a line or a queue. One electron is here and one electron is here. The combiner box just puts them in order so that the electrons come out in the marching order that they entered the combiner box. No measurement, no change in properties. It's just combining the streams. And then we'll ask some more experimental questions that involve the mirrors and combiner boxes in the coming slides. But first, is the statement of what the mirror and combiner box do clear?
Yes.
Okay, good. So now some sanity checks. So I'll ask you to predict again. Suppose we do the following experiment. We start with all white electrons. So for instance, you could think of this as, maybe we put them through a color box and keep only the electrons coming out of the white port. So we're guaranteed the input electrons are all white. So we send them into the hardness box. We split the electrons by hardness. And since these are uncorrelated, you expect again that half come out the hard port and half come out the soft port. Then you bounce them off of mirrors and recombine them. And then the question I ask you is, after recombining those two paths, if we measure the hardness, how much of the initial stream coming in do you think is hard, and how much is soft?
50% hard, 50% soft.
Good. That makes perfect sense. And in fact, this is actually true, so I'm not trolling you this time. Why does this make sense? Well, if half of the electrons come out hard and half of the electrons come out soft, and all we've done is recombine them and then measure the hardness and softness, you would certainly expect that these numbers are preserved. So half are hard, half are soft, and the numbers coming out of the ports are 50% and 50%. So there's nothing magical about this one. This is checking that mirrors and combiner boxes behave as we would expect. Okay, let's try another. So this time we start with all hard electrons, and then we measure the hardness. And since these properties are repeatable, as we said, we expect that if you feed hard electrons into a hardness box, you get 100% hard and 0% soft. So we think all of them are hard, none of them are soft. We recombine and then measure the color. So I will ask you, what fraction of the input electrons to the color box are black and which are white?
It should be 50% white, 50% black.
Good. And this again makes sense. This follows from the assumptions about uncorrelated and repeatable, right? So it's repeatable, so all of the output is hard. They're uncorrelated, so if an electron is hard, it is equally likely to be black as it is to be white. So this is true. Half of the electrons come out black, half come out white. Okay, one more sanity check. What happens here? So this time we'll start with white electrons. So again, we kind of filter by color, keep only the white ones. You feed it into a hardness box. These are uncorrelated, so 50% are hard, 50% are soft, and then we recombine the hard and soft beams and measure the color again. So don't get tricked, because we already know that once you measure this hardness, it kind of destroys property. It destroys the property of whiteness, right? We've seen before that if you measure hardness and then measure color, you're going to get 50-50 again. So if we do this procedure, white electrons split by hardness and softness, recombine, and then measure color, what are the percentages of black and white electrons that come out?
50-50.
So again, this is what you would think. 50% and 50% based on what we have said. In perhaps the most surprising sentence I've ever heard in my entire life. When you do this experiment,
Oh, it's all going to be white.
100% are white. 0% are black. This is unbelievable to me. So I'd like to dig in the next slide and see a few extensions or modifications to this experiment, but keep this set up in your head. We start with white, we split by hardness, you recombine the hard and soft streams, and then measure the color of the output, and they are all white. So let's ask what happens instead if you put a wall. So this time we're just going to literally put a brick wall in front of one of the beams coming out of the hardness box. So again, all of these are white. This is the same setup. All white electrons in, measure hardness, keep the hard electrons out of the top port, recombine those, and then measure color. So in the previous case, when we did this, we had 100% white and 0% black. Amazingly, if you put in the wall, which stops the soft electrons from leaving the hardness box rather than bouncing them off the mirror the way we did before, if you do this experiment, it's back to 50% white and 50% black. If you stop half of the electrons coming out, the soft electrons, indeed, you can measure the number of electrons that go through, and it will be down by half, right? So before, if you sent in 100 electrons, you would get 100 electrons out. Now you have half as many coming out. But of those half that come out, 50% are white and 50% are black. It gets worse, because you could imagine, well, what if there's some, I don't know, maybe the boxes aren't made especially well, and the mirrors or something, so since this is all very close together, if you put a wall in the way, I don't know, it somehow propagates a signal back to the hardness box. So it tells the electrons entering the hardness box, hey, you shouldn't exit white anymore. Now you should exit half white and half black, or something. If you're afraid that that might be the case, you can repeat this experiment where you increase the length of these arms, the distance between the box and the wall, so it's, say, 10 kilometers. You can make this as long as you want. So you can make this so long that it takes the electrons minutes to get from the hardness box to the mirrors. And if you prefer, you could even put a friend by this wall, and he can choose whether to put the wall in or take it out. So there's a wall and a mirror, and you send the electrons into the hardness box
The stream is dying.
What'd you say? The stream's dying?
Voice is getting glitchy, dropped to like 240.
Oh no, should I call back or something?
Well, let's see if it's thundering outside. Nope. I guess if you want to try recalling.
Okay, let me do that and see if it's better. One sec.
Test.
Test. Better?
I just saw lightning outside, amusingly enough.
Oh no, is the audio better?
Yes.
Okay. Uh,
Stick figures.
good. So back to the friend. You can put a friend where the wall and the mirror are, and then you can send the electrons in, and then wait so that the electrons, as they exit the hardness box, don't know whether there's a wall or a mirror at this location. So it takes them several minutes to move from the hardness box to this spot, and in that interim time, your friend decides whether to put a wall there or a mirror. Even if you do that, every time he chooses to put a mirror there, as in the previous example, they will exit 100% white and 0% black. Every time he chooses to put a wall there, which kills off half of the electrons, the soft ones, the electrons will exit half white and half black. So there's something very spooky going on here. It seems that somehow the electrons exiting the top of the hardness box, these hard electrons, they somehow know, even if it's many kilometers away, they know whether there's a wall or a mirror here. Because if there's a wall here, these electrons somehow decide to be 50% white and 50% black. And if there's a mirror here and you recombine the streams, these electrons know somehow to be 100% white. This is complete nonsense. So I'll ask one more question, and this will lead us to the introduction of a new framework for thinking, a new logical system. So let's again think about those two cases. I'll just draw them again. So the first case was you take white electrons into a color box, or sorry, it was a hardness box. Then you take the hard ones out of one port, the soft ones out of another port, and then you have mirrors. And then you combine, and then these are 100% white, right? So that was mirror challenge 3, as I called it. Now let's think about the second case, which had, again, white electrons in, measure hardness, send the soft electrons to an untimely death at this wall. The hard electrons get bounced off of a mirror and then get recombined and are 50% white, 50% black.
I've got a question.
Question.
What if your wall buddy reflects half of them?
If he reflects, sends them up into this box, you're saying?
Just, yeah.
Yeah, if the wall guy puts a mirror here, so it sends these soft electrons up into this box, then it goes back to being 100% white.
But he what if he can alternate them? So like one electron, it's reflected, the next one, it's stopped.
Oh, sure, yeah. So you could say, I mean, let's not send in a stream of electrons. Let's send them in one at a time to make sure we know exactly what's happening. So I send them one at a time. I send in one electron. This time it's a wall. So that one electron with a wall, then, I mean, you do that, then you wait, and you do that a couple times, one at a time. Every time there's a wall, one electron at a time, half of them will end up white, and half will end up black. Now you say he switches and he does a mirror. We send in one at a time, and if you do it with the mirror, every single time, even one electron at a time, they will all be white, 100%. Does that answer the question? Is that what you're asking?
But what would occur if individually putting the electrons in from one electron goes through while the wall is in, and when that first electron arrives, the wall swaps position to be a mirror
Okay, so you send one in,
for the
wait,
next
and get the
person.
result, then switch it to be a mirror, you're saying?
Yeah.
Okay, so you send the first one in with it as a wall, you wait for it to hit the end, and then that electron will either be white or black. It's a coin flip. Then you switch it to a wall, you send in another single lone electron, that one will absolutely be white with probability 1.
Okay. Yeah. Now I understand that you were trying to explain that to me, and I just didn't understand. Okay.
That's fine. It's important to recognize. So good. Let's ask this question now. So now we're going to think about the first case, the mirror challenge 3, where the electrons all exit white. And we're simply going to ask, which of these two paths did the electron take? A very reasonable question. Was the electron here, or was it here? You can imagine sending them one at a time, so there's no beam. The electron has to be somewhere. It's either here or here. We're going to rule out every logical possibility one at a time. So we send in a white electron and ask, did it take the hard path? Well, it could not have been true that this electron took the hard path to this combiner box, because when we put a wall in the way of the other path, the soft path, half of the electrons which took that path were black. So if this electron is certain to be white, it could not have taken this path because we know that all electrons that take this path are equally likely to be black as to be white. So the electron did not take the hard path. Did the electron take the soft path? Well, no. You could repeat this experiment with the wall in this place rather than down here. And then the same logic applies. This electron could not have taken the soft path because we know that if we put a wall here, all of the electrons which take the soft path are equally likely to be white as to be black. And this electron was known with probability 1 to be white. So, by pure logic, it did not take the soft path. Did the electron take both paths at once? No, you could do another experiment where you put walls in front of both paths, and you can measure whether the electron hits the wall. And every time you send in one electron at a time, you either get a beep from the detector at this path, or the beep comes from this path. It's always one or the other. The electron always hits one wall or the other wall, but never both. What other possibility is there? Did the electron take neither path? It took some other strange path besides these two? That cannot be the case, because if you put both of these walls, then the output at this detector is 0%. So if you block both streams, you get no output. So it cannot be the case that the electron took neither path, because if we block both paths, nothing gets through. So if it didn't take one, it didn't take the second, it didn't take both, and it didn't take neither, it seems that there's no other possibility for what the electron did. We are completely stuck. We're at wit's end. We literally do not have English words for the logical structure that describes what this electron did. Apparently, electrons have a new and completely unimagined way of moving, where it does not take one path, it does not take the second path, it does not take both, and it does not take neither. We simply do not have words for this because humans did not evolve to understand motion such as this. So in physics, whenever there's some new logical structure that we cannot understand with our classical intuition, we simply define a new word and work from there. So, as we'll see, the word we use for what the electron is doing is superposition. The electron moved in a superposition of both the hard and the soft paths. Now at this point, this word is completely meaningless because all we're saying is we have no idea what the fuck is going on. So we're going to define a new word, superposition, and then try to figure out what properties motion in a superposition of paths has. So there's no content here. There's no magic. There's nothing like, this is not the answer to the question. So far, this word is just an admission of ignorance. We don't know what's going on, and we need a new language to describe what the electron is doing to understand these results. Okay, questions or thoughts on this?
I have no questions or thoughts.
Good. Well, hopefully.
Also, lovable title.
It's very important. I mean, maybe you have no thoughts, but if you have no emotional response to this, then you have no soul. Man, this is one of the things when I read about this in high school that convinced me that physics was really the right thing to do, that you just had to understand this. But, okay.
But do you understand it?
I don't know, I like to think I do now. Okay, so we will need to define and kind of set up the rules of a new theory to describe what's going on with the electrons here. And just as in geometry, Euclid starts with a few postulates and then derives all of the results of geometry from those postulates, or in calculus we begin with the definition of a limit and build everything up from that definition. It's typical to start with a few postulates of quantum mechanics, which I'll tell you, and then build up all the results and explain the Stern-Gerlach experiment we've just seen using these postulates. So some of these we've seen before. I've hinted at, in session 1, this statement of postulate 1, which is the state of a physical system is represented by a vector u. So every possible state the electron can be in for this experiment will be represented by some two-component vector, although in this case it so happens that we need to use the complex numbers. So you have two numbers a and b which are both complex, and the vector of those two numbers tells you the complete state of the electron. This is the most information you could possibly know about the electron is encoded in this vector. So that's postulate 1. Postulate 2, in addition to the state of a system, there are observables, things we could measure. These are things like color or hardness. So for every observable like color or hardness, every observable I'll call A, there's a matrix which I'll represent by using the same letter as the observable with a hat over it. So if the observable is A, the matrix is A hat. So everything you can measure like color is represented by a matrix. And as we know, I've emphasized again and again, you should not think of a matrix as an array of numbers. You should think this as a function. A matrix is a function from vectors to vectors. Here C2 to C2. So a matrix takes in complex vectors and spits out complex vectors. That's postulate 2. Postulate 3, every time you perform a measurement, you measure an observable A. The only possible things you can measure, the results you get for that measurement, are the eigenvalues of the associated matrix A hat. So if we measure something associated with, say, sigma z, as we've seen, is 1, 0, 0, minus 1, and you've seen before that the eigenvalues, since this is diagonal, are just the diagonal entries, you will only be able to get the possible results of your measurement plus 1 and minus 1. Those are the only two. So we can call, say, plus 1 hard and minus 1 soft or whatever. You can put whatever names you want on them. But the point is you will only get these two possible measurements and nothing else. That's it. Okay, questions or thoughts on the first 3 postulates?
I have none.
Okay. 3 more. Now, it's not much of a physical theory if I don't give you a prediction. So I have to tell you something that lets you predict what the measurement is going to be ahead of time. Otherwise, I'm not doing physics, I'm just doing philosophy. So here's the rule of measurement. If the system is in a state U, so it's a state vector U, and we write U as a sum of the eigenvectors of a matrix A hat. So for instance, say the eigenvectors of the matrix A hat are V1 and V2. and we write u as a sum of v1 and v2. This is just like when we wrote, say, 1, 0 last time as a sum of eigenvectors of the Fibonacci matrix. So you just write u as a sum of eigenvectors of a hat. If you do that, and then you measure the observable a, which is associated with a hat, in the state u, the probabilities of the two possible outputs, which are the eigenvalues lambda 1 associated with v1 and lambda 2 associated with v2, are each going to be proportional to the absolute value squared of the complex number appearing in front of that eigenvector. So a1 appears in front of v1, so the probability of getting lambda 1 goes like a1 norm squared. We have to divide by this number. And the probability of measuring lambda 2, which goes with v2, is proportional to the absolute value squared of a2. Now you might ask, why do you divide by a1 squared plus a2 squared? Maybe you have an answer for that. Do you see why I should divide by this sum?
I have a thought, but no basis.
Okay, what's the thought?
Dumb idea. Are we possibly dividing by u squared somehow?
Yeah, exactly. So we're dividing by, this is kind of the norm of u squared in a certain sense. And the reason we do that is so that these probabilities add up to 1, right? So probability of getting lambda 1 is a1 squared over a1 squared plus a2 squared. And the probability of getting 2 is a2 squared over a1 squared plus a2 squared. Now when you measure this thing, you get something. You get some result, and there's only two possible results. So when you add up the probabilities of the two possible things you could get, you had better get 1, right? Because something happens. So the reason we divide by this is so that when you add these two probabilities, you will get, just kind of combining the numerator since they have the same denominator, a1 squared plus a2 squared over a1 squared plus a2 squared, which is 1. So that makes sense. The probabilities should add to 1 because you must get either one or the other. It's like flipping a coin. You get, I mean, even if it's an unfair coin, so it gives heads 70% of the times. If you add 70% heads plus 30% tails, you would better get 1 because either one or the other happens. So that's why we do that. And in fact, to avoid writing this because it's annoying, we will often do something called normalizing. So when I say we normalize a vector, I mean we're just going to divide by this quantity ahead of time. We're going to divide by a1 squared plus a2 squared so that the denominator is 1 and we don't have to write it. So for instance, if we're looking at the vector 1, 1, I will sometimes just normalize that without telling you and write it as 1 over root 2, 1, 1. Because if we take the norm squared of this, it will be 1 squared plus 1 squared over root 2 squared, which is 2 over 2, which is 1. So that's normalizing, so we don't have to write that denominator. Good. Is that procedure clear?
Sure.
All right. Is it actually, or are you faking?
For the most part.
Okay. Is there a question about normalizing or about the probability argument?
I have no questions.
Okay. And we will forge on, and if a question appears, you can ask. Okay, so postulate 5. This is what's sometimes referred to as the collapse of the wave function. So postulate 5 says that when you perform a measurement of an observable A, so you measure A, and as we see by postulate 4, the result of that measurement will be one of the eigenvalues of A, lambda 1 or lambda 2. Postulate 5 tells you that immediately after you perform that measurement and you get one of those two eigenvalues, either lambda 1 or lambda 2, the state of the system is the associated eigenvector vi. So if I perform a measurement and I get lambda 1, immediately after that measurement, the state has collapsed. The state has changed from u into the eigenvector v1 associated with lambda 1. Likewise, if I perform a measurement before the system was in state u, and I get the measurement lambda 2, afterwards the state has changed into the eigenvector v2. So performing a measurement and getting one of the eigenvalues changes the state, so it is now in the state of the corresponding eigenvector associated with that eigenvalue, v1 or v2. So that's collapse. The last postulate I won't say much about, because this discusses how, in the absence of measurement, the state vector will change over time. And unfortunately, we can't say much about changing in time without derivatives, which will be chapter 3 in the calculus kind of track. So I include this mostly for completeness, but we won't be able to say much about it for now. Okay, that's all the postulates. Thoughts, questions, death threats?
I have none.
Okay. All right. Let's see an example of how these work. So this property we've been calling hardness. Suppose that property is associated with sigma z, this matrix we've seen before. It's 1 and minus 1 on the diagonals. So we know the eigenvalues and eigenvectors. They're 1 and minus 1, as I've said, and the eigenvectors are 1, 0 and 0, 1. So suppose I prepare an electron in this state, u. So a state is a 2-column vector where both of the numbers are complex. So suppose the top component is 1 plus I over root 2, and the bottom component is 1 minus I over root 2. We can rewrite that as 1 plus I over root 2 times v1, because multiplying this number by 1, 0 gives me the top part, plus 1 minus I over root 2 times v2, because this number times v2 gives you the bottom part. Now, using the postulate that tells you about measurement, if I measure hardness, I'm supposed to get either lambda 1 or lambda 2 with probabilities that are proportional to the coefficients in front of those two eigenvectors, or the absolute values, I guess. So how do we compute these probabilities? Well, you have to remember how to take the absolute value of a complex number. So 1 plus I over root 2, take the absolute value squared, for instance. So this is always the real part squared plus the imaginary part squared. So this should be 1 squared plus the coefficient in front of the 1 is the I is 1, so 1 squared plus 1 squared over square root of 2 squared, right? 1 plus 1, I should have divided, shit. Yeah, sorry. Well, this will give me 1. We'll have to divide, I didn't normalize in these examples, but for the same reason, 1 minus I over root 2 norm squared will be 1 squared plus minus 1 squared over root 2 squared, which is again 1 plus 1 over 2. So 2 over 2 is 1. So these two are equal. And as we saw, the probability of getting 1, for instance, will be the norm of a1 squared over the sum of these two, which I should have set to 1, but I didn't. So the probability of getting 1 will be 1 over 1 plus 1, which is a half. And in the same way, the probability of getting 2 will be a2 squared over a1 squared plus a2 squared, which is also 1 over 1 plus 1 is 1 half. So in this example, the norm squared of both of these coefficients is the same. So the probability of getting the hard state, the hard eigenvalue, is half. You get that half of the time, and you get soft half of the time, just because the absolute values of these two complex numbers are equal. Okay, questions on this?
I have no questions.
Okay, do you remember this? I don't know if you've seen this before, this procedure of, the Absolute value of a complex number. Is this familiar?
I mean, I haven't seen it before, but it makes sense to me.
Okay, good. If you'd like, you can think of it in the plane as the complex plane where y is the imaginary part and a is the real part, and then it's just the Pythagorean theorem. It's the length of that arrow. Okay, then I will ask you to apply this to an example. So suppose, where I've actually normalized it properly this time, I prepare an electron in the state 1 over root 6 times the vector 1 plus I upstairs and 2 downstairs. So what are the probabilities of getting hard, where again, remember, hard is associated with the eigenstate 1, 0, and soft is associated with 0, 1. What are the probabilities?
So I do not totally understand normalizing.
That's fine, just divide by the sum then, since I haven't normalized it properly.
Well,
Well, what's the first step? So we express this as a sum of the eigenvectors of these two, 1, 0, and 0, 1. So don't worry about normalizing for now. Just what should I do to get the coefficients that should appear in those probabilities?
right now I'm thinking about, well, quote unquote, distributing this 1 over root 6 and then breaking that into its parts.
Okay, so 1 over root 6 gets multiplied by each of those components, you're saying? And then when you break it
Yeah.
into parts, what does that end up as?
That's going to be the word. That's going to be the vector 1 plus I over root 6, 0.
Yeah, so I'll write it like this. 1 plus I over root 6 times 1, 0, basically, right? Good. And
Yeah.
then the second one?
The second is going to be 2 over root 6 times 0, 1.
Good. Okay, so now this is a1, since that's the number appearing in front of this hard eigenvector, and this is a2, since it appears in front of the soft one. So now we need the absolute values of these two complex numbers. So what are the absolute values a1 squared and a2 squared?
Just writing stuff down right now. So let me see. So I guess we're going to recall our probability equations. I'm just writing these down now. Am I supposed to be doing scratch work, or is this something I should be able to do in my head?
I think for getting these two absolute values squared, you should be able to do it just by looking at it. So let's do a2 for instance. So a2 is this one, the one in front of the soft eigenvector. So this is just a real number. So what's the absolute value squared of 2 over root 6?
So absolute value squared of 2 over root 6 is going to be 4 over 6, or 2/3.
Good.
Yeah, I'm over here trying to do this on paper, and it's taking longer.
That's fine. I mean, okay, so how about this one? This one is,
That's going to be 1/3.
yeah, 1/3. Same reason, because real part squared is 1, imaginary part squared is 1 also, because of the I, then you divide by root 6 squared. So this is 1 plus 1 over 6, or 1/3. Good. So if you prepare an electron in this state and measure hardness, if you send it into a hardness box, it will get sent out of the hard port, the top port, 1/3 of the time, and get sent out of the soft port 2/3 of the time. Good. Okay. Thoughts? I mean, besides rage at the arithmetic, but other thoughts on this?
I don't really have any thoughts.
Okie dokie. Okay. Let's introduce a second matrix, a second observable, now associated with color. So we said that before hardness was associated with sigma z, which is the diagonal matrix 1, 0, 0, minus 1. Now let's say that color is associated with sigma x. So sigma x has these off diagonals, 0, 1, 1, 0. And we saw in a previous, I think even in one of the matrix challenges where you found the eigenvectors of one of these, or maybe this was in lecture, I forget, but the eigenvectors of sigma x look like 1, 1, and 1 minus 1. So I'm going to go ahead and normalize these two right away and put a 1 over root 2 outside, but that's not super important, because you remember that if a vector is an eigenvector, then any scalar multiple of that vector is still an eigenvector. So even if you just remember that these are 1, 1, and 1 minus 1, then these are just, some scalars times those kind of usual eigenvectors. Okay, so these are the eigenvectors of color, sigma x. And as we saw, the eigenvalues are 1 and minus 1, so I will choose to call 1 black and minus 1 white. So if the electron starts in a state of definite hardness, so this is the hard eigenstate, 1, 0, and I measure its color, to get the probabilities, I have to express this vector u as a sum of these two color eigenvectors. So to do that, I take the vector u, which is 1, 0, and I simply write it as 1/2, 1/2, plus 1/2 minus 1/2. Since obviously adding the top components of these vectors gives me 1, and adding the bottom components gives me 0. But in the way that I've written it, 1 over root 2, 1, 1, and 1 over root 2, 1 minus 1, the first vector here is 1 over root 2 v1, and the second is 1 over root 2 v2, just by comparing these. So now I can get the probabilities right away, because this is a 1, so the probability of getting the eigenvalue lambda 1 associated with a1 is simply going to be the absolute value squared of 1 over root 2, which is 1/2. The probability of getting lambda 2, which is the white color, will be the absolute value squared, again, of 1 over root 2, which is 1/2. So this is the mathematical basis for the claim that color and hardness are uncorrelated. If the electron is in a state of definite hardness, say it came from the hard port of a hardness box, and you measure its color, then the two outputs are equally likely, 1/2 and 1/2 for black and white. It's simply a statement about eigenvectors. Okay, questions on this?
I do not have any questions.
Good, more than. Okay, so now we'll walk through kind of repeated measurements, not unlike that first challenge where we have 3 boxes in a row. So I'll ask you. We start with an electron in the state 0, 1, which as we've seen is the minus 1 eigenvector of sigma z, which is definitely soft. So remember, sigma z is 1, 0, 0, minus 1. Sigma x is the one with off diagonals like this. So the state 0, 1 is the minus 1 eigenstate of sigma z, which we're calling soft. So if I measure color, Remember, color is associated with sigma x, and the two eigenvectors of sigma x are, well, I should normalize, 1 over root 2, 1, 1, and 1 over root 2, 1 minus 1. I will ask you, if I measure color in the state of definite softness, what are the possible outcomes and their probabilities?
So sure, the possible outcomes and probabilities are going to be a 50-50 mix of the former 1 over root 2 times vector 1, 1, and the other 50% is going to be 1 over root 2 times 1, negative 1.
Good, although we should say it's 1 over root 2, 1, 1, then I think minus 1 over root 2, 1 minus 1, right? We're trying to write 0,
Okay.
1. Yeah, see what I mean? Since we want the top to be 0, so 1 minus 1 with a root 2 is 0. 1 minus a minus 1 will give us the 2 over root 2. So up to normalization, this will give us the 1 downstairs, right? Okay, so yeah, I agree though. Since now the two coefficients in front of these things are 1 over root 2 and minus 1 over root 2, but we take absolute values to get the probabilities. So I agree, the possible outcomes are 50% white and 50% black. Okay. So now suppose we perform that measurement in 1. So the electron starts soft, I measure color, and the output of that measurement is black, where we remember that black is associated with the first eigenvector and white is associated with the second eigenvector. So after I measure the electron and find it black, what state U is the electron in after the measurement?
According to the slide, a few slides ago, it should be in V sub I,
Right,
but
so
I don't know what that is. Or the black. Yeah, or the black eigenvector. But I don't know which one that is.
So black, as I've written here, is the V1, right?
Oh, okay. Yeah, I missed that. Good job, Self. Yeah, it's going to be 1 over root 2 times 1, 1.
Good. So the electron started in 0, 1, definitely soft, and then I measured the color, got black, and that has changed the state of the electron. It is now in the state 1 over root 2, 1, 1. So now the last question, after performing that measurement and getting black in step 2, I now measure hardness again. Well, remember, hardness is associated with the eigenvectors of sigma z, which are 1, 0 and 0, 1. So what are the outcomes and probabilities of the hardness measurement in this state?
Thinking. So I believe we are given that, yeah, U equals 1 over root 2 times 1, 1. So we need to figure out a way to break that into its parts.
Yeah, so how do you write this as a sum of two vectors, one of which is proportional to 1, 0, and one of which is proportional to 0, 1?
I guess you could just do that. That is equal to the sum of 1 over root 2 times 1, 0 plus 1 over root of 2 times 0, 1.
Good, okay.
Yeah.
So 1, 0 was hard, and 0, 1 was soft. And the probabilities are proportional to the norm squared, the absolute value squared, of these coefficients. So what are the probabilities of hard and soft?
Thinking. And that's a dog. Okay. Yeah. The probability of the former hard is going to be 50% since the absolute value of 1 over root 2 squared equals 1/2.
Good.
And similarly, the probability of soft is going to be 1/2.
Or a half, 1 over root 2 squared.
Yeah.
Good. Okay. So this, although the math perhaps is fairly simple, this explains, or I don't know if explains is really the right word. This is a model. This is consistent with the results of the first surprising Stern-Gerlach experiment, where we first measured color. You sent an electron, say, through a color box, then a hardness box, then through a color box again. And after measuring, say, the hardness of electrons which were known to be black, or vice versa, then you had a 50-50 chance of getting electrons whose first characteristic disagreed with the output of the first box. Right, so I send in, say, all soft electrons, measure color, keep the black ones, and then measure the hardness of those supposedly soft and black electrons. But surprisingly, half of those electrons have now become hard rather than soft, even though all of the electrons fed into the first box were known to be soft. So I'm not claiming that this really gives you the full story, but it is at least true that if we assume that this matrix model describes the way that electrons move, then the output of this kind of mathematical procedure is consistent with the output of the experiment, right? So this explains, in some sense, why measuring color of soft electrons and then measuring hardness again will give you electrons that are half the time hard. Okay, other questions?
I have no other questions.
Good. More than. Okay, so allow me to emphasize this once more, since this is really quite key. The real, I guess, takeaway from, I think it was postulate 4, and from this example, is that measurement always changes the state of a quantum system. So as we saw in the previous example, when we measured color and got black, for instance, even though the electron began as soft, the performing of the measurement which gave black changed the state to this u equals 1 over root 2, 1, 1, which is known to be black. So the electron which started as soft and was measured black no longer has a definite hardness. So the punchline of all of this is that we can never simultaneously know both the color and hardness of an electron. If you wanted to know for certain that an electron were both, say, black and soft, then that would mean it had to be an eigenvector, both of those two matrices, sigma x and sigma z. Right? Because to know that it is black means that it is in one of the black eigenstates of sigma x. To know it's soft means it's in one of the soft eigenstates of sigma z. So to know that it has both properties at once, it would have to simultaneously be an eigenstate of those two matrices. But as I'll show on the next slide, there are no vectors which are eigenvectors of both of those matrices at the same time. So this is behind the statement of uncertainty. The statement that you can't simultaneously know color and hardness is really just the statement that a vector cannot simultaneously be an eigenvector of sigma x and sigma z. And just to emphasize a philosophical point, you might think, well, this is really no different from a classical system. Suppose I take a box and I put a d20 in the box and I shake the box a lot, so it's, I don't know, you shake this up and then you don't know which side is up on the d20 and you don't open the box. So in this case, the d20 has some state, perhaps 17 is the side facing up, but you don't know what the state is. And then when you open the box, you open this up, and then you know, aha, the d20 is in the state 17. You might think that that situation is similar to the electron with color and hardness. That, I don't know, it was in a soft state and it had some hardness, just as the d20 had a number before I looked in the box, but I didn't know what I don't know, the color of the soft electron was. But these two systems are fundamentally different. These are not the same. The D20 in the box had a definite state. It was in the state 17, and I just didn't know what that state was. And opening the box and looking at it and seeing that it was in the state 17 was only informing me of something which existed prior to my looking in the box. That's the classical case. Classical. The system had a state. There was a definite answer, and I didn't know what it was. In the electron case, when it was in the state soft, and I measured it, it's not the case that the electron had a color, and I didn't know what it was. Before I measured the color, the electron was not in a state of definite color, so there was no answer to the question, what is the color of this electron? It was just a nonsensical question. It would be like, were the dreams you had last night recursive or imperative? That question doesn't make any sense. Python programs have the property of being recursive or imperative, but human dreams do not, right? That property is not something you can assign to an electron which is in a state of definite hardness. But then when I measured the color of the electron, it changed the state. So it was now in a state of definite color. That's the difference. In the classical case, the D20 had a number and I didn't know what it was. In the quantum case, the electron had no answer for the question of what is your color until I measured it, and that changed the electron so it did have such an answer. Very different. Okay, questions on that?
I like your and suddenly dogs. I want to mention cats. Beautiful. I like how you mentioned a D20 instead of Schrodinger's cat. I didn't pronounce that right.
Oh, the Schrodinger cat experiment?
Schrodinger, yes.
Yes. Well, yeah, the D20 is the classical case. The Schrodinger's cat is supposed to be the quantum case, but yes. Is the difference between having a property which I don't know and not having the property at all totally clear?
Sorry, did you ask a question?
I did. I was just checking, is the difference between having a property which I don't know and not having the property at all very clear between these two cases?
Yes.
Okay. Alright, so we're almost done. I would just like to make this slightly more mathematical. So I claimed we can't simultaneously know color and hardness because these two matrices don't have simultaneous eigenvectors. You can't have a vector which is simultaneously an eigenvector of sigma x and sigma z. And I'd like to connect that to something we saw in session 1 with the commutator. So the reason there's no eigenvector of both matrices at the same time is because they don't commute. And the reason for that is the following proposition. So suppose these two matrices A and B, which could be sigma x and sigma z if you prefer, share an eigenvector v, which means v is an eigenvector both of A and of B. If that's true, I claim that if you take the matrix commutator of A and B and apply that matrix to the vector v, you'll get 0. Okay, so why is that? The proof is that you suppose A and B both have the eigenvector v. By the definition of eigenvector, that means A on v gives you a number times v, which I'll call lambda a. B on v gives you another number, which I'll call lambda b times v. And now we'll just compute the commutator. The commutator is ab minus ba. So if you take ab on v, well, b on v is lambda bv, and then a on v is lambda av, so that's simply lambda a lambda bv. If we go in the other order, it doesn't matter, because a on v is lambda av, and b on v is lambda bv, so this gives us the same thing, because although matrices don't commute, multiplication by scalars, just regular numbers, certainly commutes. So the commutator ab on v is simply lambda a lambda b on v minus lambda b lambda a on v, which is 0. So the point of all of this is that if there is a state which has a simultaneously well-defined property associated with these two observables, so if A and B are, say, color and hardness, if there is ever a state that has a well-defined color and a well-defined hardness, then the commutator of those two matrices applied to that vector must be 0. But as you showed in Matrices Challenge 1, I think, sigma x, sigma z, I think is proportional, well, this is in the wrong order, so it's minus 2i sigma y, which is not 0. So this is why this can't happen. If these two things shared an eigenvector v, then we would need sigma y applied to that v to give us 0. But sigma y is not a non-zero matrix. So you're not going to get a non-zero vector such that sigma y applied to that vector gives you 0. So the fact that these two matrices don't commute is the fundamental reason why you cannot simultaneously know the color and hardness of an electron. Okay, questions on this?
I have no questions.
Good. Okay, so I guess I can go through this somewhat fast since I don't think there'll be a Matrices Challenge 4. But you might ask if there's an easier way, rather than rewriting a vector every time as some linear combination of the two eigenvectors, say, this plus 1/2 times 1 minus 1. You might ask, if I'm going to measure something, is there an easier way besides expressing this as a sum of the eigenvectors and then taking the absolute value squared of each of these numbers? And there is, and if we had more, I guess, time for the matrices unit, I would spend a lot of time on inner products, because these are quite important. So the idea of an inner product is a function that takes in two vectors and gives you a number. So it's usually written with angle brackets like this, angle bracket UV. And there's many types of inner products, but the most useful one for quantum mechanics is the one I've written here, which is that if U is a vector U1, U2, and V is a vector V1, V2, which are all complex numbers, then you take these two vectors and spit out the number, which is the complex conjugate of U1, the top component of U, times V1, plus the complex conjugate of U2 times V2. So remember, complex conjugate is just if Z, a complex number, is A plus BI, the complex conjugate reverses the sign on the imaginary part. So this function simply takes the components of two vectors and multiplies the complex conjugate of one times the other and adds them. Sometimes we use a mnemonic for this, that the dot product or inner product of two vectors is written with this conjugate transpose, or dagger. So if U is a vector with two complex numbers, U1 and U2, you can write U dagger in this kind of strange way as a transposed or flattened rather than tall vector, U1, U2, where we've taken the complex conjugates of both pieces. So if you write it this way, then the inner product U and V is written as this U dagger V. And the reason that's nice is because we can use the usual mnemonic for matrix multiplication. You take a horizontal line times a vertical line, and it gives you U1 complex conjugate times V2, or V1, which is the first piece, and U2 complex conjugate times V2. That's the idea, but one should be very careful because, as I've emphasized, matrices are not just arrays of numbers. A matrix is a function, a vector is an element of C2, and this strange kind of long vector, rather than a tall vector, actually lives in a different set from regular vectors. This is something called the dual space of the usual vector space, which, again, given more time, I would define this properly and tell you what a dual space is. But for now, you can just think of this as, well, I don't know what a dual space is, but I remember the mnemonic, so I know how to multiply these things, and it gives me a number. And if you remember that, then the probability of measuring one of those eigenstates lambda in a state U, you don't have to do all of the work of expressing U as a sum of eigenvectors of, say, the matrix A hat. You can just use this mnemonic and take the inner product, U dagger V, and take the absolute value squared. Okay, so that probably sounds very mysterious. I will show one example where we do this, and it's the same example from before, in fact. So if we're in the state U, which is 1 over root 6, 1 plus I, and 2 from before, where we worked this out carefully in a previous example, the probability of measuring black, where black is this eigenvector, well, that's U dagger V, which means we take the complex conjugate. Complex conjugate means we reverse the sign on the imaginary part. So 1 plus I, 2, and 1, 1. Then I take the constants, 1 over root 6 times 1 over root 2 is 1 over root 12. And now I multiply these, 1 minus I times 1, and 2 times 1 gives me 3 minus I over square root of 12. So that's what I've written here. It's I haven't combined the 2 and 1, but this is 3 minus I over root 12. And then the probability is the absolute value of this thing squared. So probability of black, the absolute value of this thing is real part squared is 9 plus imaginary part squared is 1 over 12, which is 10 over 12 is 5/6. Similarly, the probability of getting white, you can do the same game where this was V1 up here. Now you can take U dagger V2, which again will be 1 over root 12. U dagger is 1 minus I2. V2, remember, was 1 minus 1. So now this will be 1 minus I minus 2. Let's see. Yeah, 1 minus I minus 2. The 1 minus 2 gives me a minus 1, so it's minus 1 minus I over root 12. And the absolute value of this thing, real part squared plus imaginary part squared, is 1 plus 1 over 12, and 2 over 12 is 1/6. So this is rather faster than expressing this as a sum of eigenvectors. You can take inner products, and it kind of does some of the work for you. Okay, a bit fast, but questions on this?
I have no questions.
Okay. Good, good. A few teasers, and then I will conclude. So, I haven't told you much about inner products, but there's a lot to say about these. Morally speaking, the inner product kind of tells you how aligned these two vectors are. If the two vectors are the same, for instance, if you take the inner product of a vector with itself, and it's going to give you somehow the length squared of that vector. So maybe that's less intuitive for complex vectors, but for real vectors in the plane, which, just arrows, directed line segments, for instance, in R2, then this inner product is sometimes called the dot product. So A dot U, you just take the first component of A times the first component of U and add the second component of A times the second component of U. And geometrically what this does is it projects the vector A onto U. So it's kind of taking the vector U and asking how much of A points along U. It's taking the part of A that points along U, which is this part. And just by geometry, you can see that's going to be, using trigonometry, this is going to be the length of A times the cosine of the angle theta here between A and U. So for real vectors, this inner product or dot product will tell you what is the angle between two vectors. And you can use this to give a very fast proof of, for instance, the law of cosines, which we proved a while ago. This was the generalized Pythagorean theorem, where c squared equals a squared plus b squared minus 2ab cosine of the angle gamma associated with c. So you can prove that very quickly with dot products, but I will not show you how to do that. So last two things. One, way back in session 1, I told you about this uncertainty principle. And hopefully most of the pieces we can now understand. I told you in session 1, anything you can measure is represented by a matrix. That was postulate 2. I told you the state of a system is represented by a vector. That was postulate 1. And then I wrote down this uncertainty principle, which is simply the statement that you cannot get an accurate measurement for the observables A and B at the same time if A and B don't commute. And now we know what all of these symbols mean, right? The commutator of A with B is a matrix. So this is saying take the vector U, act on it with the matrix A commutator B, take the inner product with U dagger from a previous slide, which gives you a number, and take the absolute value of that number. And this is something which will be a larger number if A and B don't commute, and 0 if they do commute. And here what I mean by error or uncertainty in a measurement is really just the standard deviation you learn about in, say, Algebra 1. Right? The standard deviation, sometimes written sigma, for instance, sigma A. You just take the average value of A squared minus the average of A quantity squared. So, for instance, if you're in, I don't know, the state 1 over root 211, and you measure hardness, you'll get half the time hard, which is +1, and half the time soft, which is -1. So the average value of A is 1/2 minus 1/2 is 0, so average value of A is 0. But the average value of A squared is always 1, so the average value of A squared is 1/2. So you would get this 1 over root 2, square root of 1/2 minus 0 for sigma A. This is the statement of the uncertainty principle. It's really all about non-commuting matrices. And a final teaser, you could reasonably ask, because I've said several times, something about preparing an electron in a state. I was intentionally vague about this. So you could ask, what do you mean by preparing an electron in a state? How do you change the state of an electron to be in some vector u that you'd like, say AB? Because the only way you've told me to do that is by measuring it, and measuring it always collapses it into an eigenstate. So how would you prepare it into some arbitrary state AB that you want? And the answer is that this is closely related to time evolution, postulate 6, which I said very little about. So I'll say slightly more about it. More quantitatively, postulate 6 is the Schrödinger equation, which is this equation here. This is the Schrödinger equation, which is telling you that the way that a state vector u changes in time, which is encoded by this weird ddt symbol on the left, the way it changes in time is described by a particular matrix H called the Hamiltonian acting on u. So the way u changes in time is described by a matrix acting on u. But the reason I've been very vague about this is because we cannot at this point understand what this meaning of this du dt really is. Because, as I alluded to in the rocket equation preview, basically everything in physics is a differential equation. And this Schrödinger equation is no exception. Du dt is short for a particular limit as a delta t goes to 0 of a function of u of t, which we will see in chapter 3. So this is very mysterious for now, but eventually we will be able to understand this once we know what derivatives are and know how to take the derivative of a vector, for instance.